wonderful event. It's just delightful to be with all of you here today. Given the proximity of today's date to Pi Day is March 14th, just 4 days away, I thought I would give you a little presentation about the number pi, and a topic presented itself to me because just last year, a new record was set for the computation of pi. A team in Switzerland computed almost 63 trillion digits of pi. To give you some idea of the magnitude of this accomplishment, this book, Pi Reference, contains the first 1 million digits of pi. The book is 400 pages long. Each page has 2,500 digits, arranged neatly in rows and columns, like so. If all the known digits of pi were printed into books of this size, you would need almost 63 million such books. If you were to stack all those books one atop the other, you would get a pile that would be about 1,000 miles high.
Super high.
If you were to replace every book in the Freedsome Library with a book of comparable size but containing only digits of pi, and Lord knows I've asked, Penguin says no. You would need about 100 Freedsome Libraries to hold all the known digits of pi. Today I'm going to share with you a bit of the history of the computation of pi to explain how this staggering achievement was possible. As we go along, by the way, if you've got any questions, just let me know. You don't have to wait till the end. Oh, it's not working because I didn't put in the magic device. Hang on. Let's see this one out. There we go. So we'll begin with a little background about the number pi, some of the fundamentals. The calculation of pi falls neatly into three eras. There's the time, a long time ago, when pi was being calculated without the benefit of calculus and without the use of computers. And then calculus came along and got soon used to calculate pi to an even greater accuracy prior to the use of computers, still computing by hand. And then finally, the era in which we live, the calculation of pi using calculus and computers. Please note that no previous knowledge of calculus is needed for this talk. We'll conclude on a note of humility. Despite the enormous success that there has been in calculating the digits of pi, there are some very basic questions about the number that remain unanswered. Let's begin at the beginning with what the number pi is. Pi, often called the circle constant, is by definition the ratio of a circle's circumference to its diameter. The circumference is the distance around the circle, and the diameter is the distance across. This gives us, the definition actually gives us one way to compute pi, potentially. Take your favorite circular object, such as...
diamond ring.
That's a really nice circular object. I have another one in mind, possibly appropriate for this audience. Measure its circumference using, say, a cloth tape measure. Measure its diameter using a ruler, and divide. Unfortunately, this method is unlikely to give you very much accuracy in your calculation of pi due to the errors that are inherent in physical measurements, and also due to the fact, and the second point I'm hesitant to make in front of this crowd, this is not a perfect circle. It's a nice circle, so I hear. Not so much for me. But it is not a perfect circle. No physical circular object is a perfect circle, so henceforth, with one notable exception, we will be calculating pi by the benefit of theory and not with measurement.
Chris, can I ask a question?
Absolutely, yeah, Jimmy.
So is there, so like, we got this, like standard, mass per kilogram. Is there, in mathematics, like almost a perfect circle that people that you guys have, or?
I've certainly read about, in physics, objects that were very close to perfect spheres. Really absolutely incredible engineering feats where they would polish a sphere to great precision so that it was very, very nearly a perfect sphere. So perhaps that would be the closest analog of something of that type. Circles being flat, it might be easier to create a three-dimensional object than a flat perfect circle. But definitely, if you Google that, you'll see some amazing videos about that.
Thank you, Chris.
You're welcome. We can actually track the use of the Greek letter pi for denoting the circle constant back to 1706, when William Jones first used the symbol, possibly for the word periphery. But it wasn't until the great Swiss mathematician Leonard Euler adopted the notation that it really caught on. One of the most remarkable aspects about the number pi is its ubiquity in formulas. Certainly, it appears in formulas where you'd expect it to appear, in the measurements of circles or circular-like objects. You've got the circumference of a circle, area of a circle, volume of a sphere, surface area of a sphere, and the volume of a cone. A cone has a circular base. But pi also pops up in math formulas where the connection to circles is less clear, if not positively obscure. For example, up here in the upper right, that, for the folks who've done some statistics, that is the formula for the normal distribution. It is the single most important distribution in all of stats.
Yep.
The number pi appears in its formula. Down here is a formula called a Fourier series. This is used by researchers to model phenomena that repeat over time. Anything from the planets circling the sun to the beating of a human heart. You'll see the number pi appearing in the formula for a Fourier series. Pi also pops up as like an answer or part of an answer to certain formulas, very surprisingly, like this one down here. On the right-hand side, there's 1/4 of pi. On the left side, it's a computation involving the odd integers. It's remarkable that you can actually calculate pi or relate pi to something as simple as the odd integers. They appear here in the denominators of these fractions. The numerators are all 1. And what we've done is taken an alternating sum of these reciprocals of odd integers, first adding and then subtracting. And if this is done forever, you get exactly 1/4 of pi. This is far from obvious and absolutely gorgeous, one of the prettiest formulas for pi ever found. And in fact, the object on the left-hand side, this fellow, is an example of what's called an infinite series. Infinite series turn out to be a major avenue by which pi can be computed. So we'll return to those shortly. Also, pi shows up in formulas and disciplines allied with mathematics. Jimmy, this is for you. Ty, this is for you. A collection of physics formulas right here. Coulomb's law for the electrostatic attraction between charges. Heisenberg's uncertainty principle from quantum mechanics. The Schrödinger wave equation, also from quantum mechanics. And from general relativity, Einstein's field equation, all involve the number pi. Last, but definitely not least, what I consider to be the single most beautiful equation in all of mathematics. This equation right here in the middle, first discovered by Leonard Euler, this was the fellow we met a few moments ago, relates the 5 most important numbers in mathematics and no others. The 5 most important numbers in math: 0, 1, the circle constant pi, e, which is fundamental for measuring exponential growth, and I, which is the square root of -1, so-called imaginary unit. This beautiful simple formula relates those 5 numbers perfectly, proved by Euler using calculus. Now on this slide, it's a little background about types of numbers. This is about all the background to leave for this talk. When we talk about real numbers, just think of any number that can be expressed using a decimal. Really any number that you use in your life or that you read about, unless you're a mathematician, you might think about other things, but are likely to be real numbers. Rational numbers are those special real numbers that can be expressed as ratios of integers with a non-zero denominator, like 7/4 or 11/12. What's nice about rational numbers is that their decimal expansions are very, I should say, predictable. They either terminate, like 7/4 is exactly 1.75, and the decimal expansion terminates at the 5, or they go on forever, but they settle into a repeating pattern. Like 11/12 is 0.91 and then 6 repeating. Either it terminates or it repeats eventually forever. An irrational number would be all the other real numbers, which cannot be expressed as a ratio of 2 integers, and more to our point here, its decimal expansion neither terminates nor eventually becomes repeating. We can thank a fellow named Johann Lambert, who in 1761, in one of the early successes of calculus, used calculus to prove that, in fact, pi is irrational. That means that pi is not the ratio of two whole numbers, but more relevant to our discussion here today, its decimal expansion neither terminates nor settles into a repeating pattern. And that makes computing pi interesting. No matter how many digits of pi you compute, you've not somehow captured the whole story. Hence the title of this talk, Infinite Quest. It's a quest that never ends. One convention that I'd like to share with you as we talk about approximations for pi, when you're counting digits of pi or we're talking about approximations, we ignore the initial 3 and then just count digits afterwards. So for example, back in your high school or middle school days, you may have learned that 22/7 is a pretty decent rational approximation to pi, 3.142857 and so forth. It gives you 2 digits of accuracy, the 1 and the 4. 3.1419 gives you 3 digits of accuracy. Thanks to, let's see, the 9 after the 1 would lead us to round to 3.142. And in pi, if you also rounded to 3 digits, you'd have 3.142. And finally, pi is about 3.14159.265. That gives you 8 digits of pi and everything you need to know about when the Pi Day celebration is at the Department of Mathematics. March 14th, starting at 1:59 p.m., lasting for 2 hours, 65 minutes. What I'm about to say next is the most important thing I'll say tonight. You are all invited. Come to Pi Day. Free pie. The other kind. Now we'll begin with the era of calculus, computing pi, estimating pi, and we'll go back 2,300 years. Archimedes of Syracuse. Archimedes developed a very elegant geometric method for approximating pi. Imagine a circle of radius 1, or diameter 2, a so-called unit circle. What Archimedes did is that since measuring round things is hard, but measuring straight things is easier, he approximated the circle using a polygon inside the circle and a polygon outside the circle with the same number of sides. I'm illustrating this with hexagons, 6-sided polygons. The green hexagon is a so-called inscribed hexagon, and outside is a circumscribing hexagon. Now the perimeter of the inner polygon is less than the circumference of the circle, which in turn is less than the perimeter of the outer polygon. If I now divide that equation by d, the diameter, in the middle, I get c over d, that's pi. And on the outside are 2 computations that Archimedes was successful in approximating. He ultimately used 96-sided polygons to estimate pi between 223/71 and 22/7. If you convert those decimals into fractions into decimals, you get these values here, and then if you average them, you'll get an even better estimate for pi, which is somewhere in the middle, about equal to 3.1419, 3 decimal places of accuracy. Interestingly, Archimedes' method of approximating polygons or using approximating polygons to compute pi remains the state of the mathematical art for computing pi for the next 1,800 years.
Wow.
It will not be until the invention of calculus that someone comes up with a better idea. So in the meantime, the hunt is on. Here's Archimedes, 250 BC, 3 digits. In 150 AD, Ptolemy computes an extra digit of pi by using Archimedes' method, and polygons with 360 sides. Please note that for using this method, you don't actually have to draw these polygons. You can just deal with them mathematically. So these higher numbers of sides can be dealt with mathematically if you've got enough patience. In 1430, Alcatia, I'm saying that name correctly, used Archimedes' method with polygons with in excess of 800 million sides. to extract 14 digits of accuracy. It's extraordinary accomplishments by hand. And the ultimate manifestation of this technique occurred in about 1600 when Van Heuvel computed fully 35 digits of pi using polygons with about 4.6 quintillion sides.
Wow.
Mercifully, it is at this point that calculus is invented so that we can stop with the polygons and use it. This takes us to the second era of calculating pi, the era with calculus, but we're still long before the invention of the computer. Calculus is the mathematical study of change. It's really superb for helping to predict things that are changing over time, which in our universe is just about everything. It is built on a fundamental technical concept called a limit, and the principal objects of study are the derivative, the definite integral, infinite sequences, and infinite series. For the purposes of this talk, it is that last object, infinite series, that will serve us particularly well for approximating pi. Oh, and I should give props to Isaac Newton and Gottfried Leibniz, who independently developed the fundamentals of calculus in the 1600s. Calculus was further refined by numerous other mathematicians over the next few hundred years. An infinite series is a summation of infinitely many real numbers. I've written a template for an infinite series in two ways. On the left side, just a list of subscriptive numbers. Each one represents a real number. The summation goes on forever. And on the right side, a compact way to express that using summation notation, sigma notation. Now, at first glance, such an object, an infinite series, sounds like the stuff of science fiction. It just sounds like it couldn't possibly be meaningful. After all, no human or not even the world's fastest computer can literally add up infinitely many numbers. However, human beings and computers can add up a lot of numbers, so you can actually physically get close to the answers to these series. And I will simply say that this technical concept of a limit, that is the foundation of all of calculus, helps us to deal with this unending summation effectively. But I would like to say, before leaving the slide, that infinite series are not so odd after all. I can give you some examples pertaining to things that you're well familiar with. I claim that I can create and sum this series here by just walking across the room. So apologies to folks following me on Zoom. I might be out of frame briefly. All I'm going to do is walk from one side of the room to the other. I'll start here and take a slightly crooked path to get to the other side because of the table. Think of the distance between myself and the far wall, the width of the room, as one unit.
You walk like Tyra Banks?
No. Easiest question I'll get all night. Think of that distance as one full width of the room. As I walk across the room, at some point I will reach the halfway point, right there. Right about here or so. Now from between here and the far wall, there is a further halfway point between myself and the wall, and once I reach that, I will have covered an additional 1/4 of the full distance. Right there. Between myself and the wall, there is a further third halfway point, and once I reach that, I will have traversed an additional 1/8 of the total distance. Right there. And so on. Between one wall and the other, I'll actually traverse infinitely many halfway points, each one half as far as the other, and once I reach the other side of the room, like so, I will have tallied up this infinite series of halfway distances, which evidently equals exactly 1. In addition to that, any repeating decimals that you're familiar with, like back in the day we all learned that 1/3 is 0.3 repeating. Embedded or implicit in a repeating decimal is an infinite series. 0.3 repeating means 3/10 plus 3/100 plus 3/1000 plus 3/10,000 plus 3/100,000, and so on forever. Evidently, that infinite series tallies up to be exactly 1/3. This then gives us a really powerful method for calculating pi. The infinite series method goes like this. Derive, somehow, an infinite series that converges to pi, or equals pi, or a closely related number. We would be satisfied if the series equals pi over 4 or 1 over pi, just pi or something very closely connected. Then add up many terms of the series by hand. If you're living in the era before computers or with a computer, as we are now, and what you get will be not the exact value of pi, which would require the addition of all the terms, but you'll get close, depending on how many terms you have the patience to compute or that you let the computer run for however long to calculate. I should point out that there is a ready-made infinite series that converges to pi, but it's positively awful for calculating its digits. It's the one that comes right from its decimal expansion. 3.14159 means pi is exactly 3 plus a tenth plus 400 plus 1,000 plus 900 thousandths, and so on. Terrible for calculating pi because in order to add up the terms, you got to know the digits of pi, and that's what you're trying to figure out. So when I say derive an infinite series that converges to pi, we understand it needs to be one in which the terms have a discernible pattern. We can understand and compute them. I'll now return to that formula for pi over 4 that popped up on one of the earlier slides. This gorgeous equation that relates 1/4 of pi to reciprocals of odd integers. This was discovered and rediscovered by fully 3 mathematicians, at least. Unfortunately, despite how beautiful it is, it's really bad for computing pi. And the reason is, its convergence is excruciatingly slow. In order to get, let's say, 10 digits of pi, and please note that fellow Van Kuylen computed 35 digits using the polygons, but just to get 10 digits of pi, you'd have to add up about 5 billion terms. This series is derived, by the way, from the infinite series for the arctangent function of trigonometry. And what a fellow named Maschen did is he used that original arctangent series and then finessed it in a very clever algebraic way to derive a different infinite series, converging to pi, but for one that has much better convergence. This series down here has, in its terms, these exponentials in the denominators, 5 to the n and 239 to the n. Those exponential denominators pull the terms down to 0 very fast, which means you don't have to add up so many of them to get decent accuracy in your approximation. Maschen calculated, and think of this is done by hand, 100 digits of pi in 1706 by adding up terms of the series that he found.
I bet he made his grad students do it.
If so, that's not mentioned in Wikipedia.
They didn't get credit for it.
Isn't that like a feather, a quill with an ink? Because this wasn't a pencil that he was using, right?
I think you're right.
Right.
Yeah. I don't know when pencils were invented, but probably not back then. Yeah. But in terms of the ultimate computation of this type for computing pi, William Shanks takes the cake. Because in 1874, he computed, using Maschen's series, over 15 years, 707 digits of pi. Unfortunately, or gratefully, at digit 528, he made a mistake. And that infected the rest of the digits. But even so, he smashed the previous records and calculated 527 correct digits. This record stood until 1947. Can you guess what happened in 1947 that finally allowed this record to be supplanted? That's right, the first computer gets used. But until then, the record stands, and in fact, it wasn't until computers got used that Shanks' error was even found. Oh, at this point, having traversed over 2,000 years of pi calculating history, I propose taking a brief commercial break. I'd like to share with you a method for computing pi that has never set any record ever. Its elegance is exceeded only by its appalling inefficiency, but I dearly love it. And this method, several of you helped to participate with me to do. Imagine an infinite grid of parallel lines, and a needle whose length, this is highlighted in red, is exactly the common distance between the lines. I have a model of this situation right here on this tablecloth. made by a friend to Specs some years ago. The person was a really excellent sewer and made a beautiful tablecloth with parallel lines that whose common distance is very close to the length of this toothpick. Several of you helped me to then emulate this problem of tossing the needle or the toothpick onto the grid randomly. And when you do so, sometimes the needle ends up between the lines, not touching any of them, and sometimes it ends up touching one of the lines. If you toss the needle many times in a row, as all of you helped me to do, some of the times it will end up touching a line, and some of the times it won't. This is 10 tosses of the needle, and among them, let's see, we got a hit of a line here, here, third one there, fourth, fifth, 6 of the 10 tosses in this case ended up touching a line. Four did not. Now here's how this relates to pi. Using a bit of calculus, one can show that the theoretical probability that a randomly tossed needle would end up touching a line is exactly 2 over pi. It's a very pretty formula involving pi. The reason that pi arises is that whether or not the needle ends up touching a line hinges on 2 things. The position, the vertical position of its center, and the angle in which it ends up tilted at. And those angles range over a full circle, and once you have circles, pi is not far behind.
Genius.
Indeed. This then gives us a way to approximate pi in the following way. If you actually physically toss a needle to this grid and track how many tosses end up touching a line and divide that by the total number of tosses, you'll get what's called an experimental probability for the needle touching a line, and that will be approximately equal to the theoretical probability, with the approximation getting even better the more tosses you make. Now, here's the only math I'm going to ask us to do this evening. Let's solve this approximation for pi. Take the pi in the denominator on the right-hand side, multiply it to the left-hand side, take the number of tosses that touch a line and divide that to the right-hand side where it pops up in the denominator, and take the total number of tosses and multiply that to the other side, where it ends up in the numerator, giving us pi is about equal to twice the number of tosses divided by the number of tosses that touch a line. Incidentally, if you would like to play around with this a bit more, there's a really cool website that allows you to simulate what's called Buffon's needle problem digitally by going to this website here, indicating by that QR code. Now, all of you, many of you, made some tosses, and I tried my best to keep track of the data correctly by tracking how many tosses total were made and how many of those ended up touching the line. And now, for the results, drum roll please. We got 51 total tosses, of which 39 were a hit. Plugging into our formula, we get an approximation for pi equal to 2.63, which, for the method used, is not completely awful. If you round that to the nearest whole number, you get 3, and that's the right whole number. This method is really awful at computing pi.
I wish.
You have to really do a lot of tosses before you get even a few digits of pi correct. You can really see this in a striking fashion from that website, which allows you to do like 1,000 or 10,000 random tosses in the blink of an eye. All right, thank you for that brief commercial break. Heading back now to the final era of pi calculation, in which we live, where we have the benefit of calculus and computers. I can summarize this era with the following equation. Calculus plus Moore's law gives us lots and lots of pi. Gordon Moore was a computer scientist, he's still alive, is a computer scientist, who decades ago made a striking prediction about the evolution of computer hardware. He predicted that the number of components, think transistors, on an integrated circuit would double about every 2 years. Now, interestingly, the computer industry took that prediction as a goal, and they strove to actually build computer circuits with double the number of components, double the number of transistors every 2 years. And because of that, it became a kind of self-fulfilling prophecy. Moore's law has held really well in the years since. Just now, and maybe my physics friends can confirm this, I think it's starting to break down because we're coming up against the physical limitations of actually packing so many things into a small space. Quantum mechanics has something to say about it when you pack so many small things into a small space. And this now brings us to the first time a computer was ever used to calculate pi, 1947. 2,037 digits were computed using the ENIAC, first electronic computer ever made. This, my friends, is what a computer looked like back in the day. Fills a room. This is before transistors were invented, so it's filled with vacuum tubes. And now watch the explosion in the number of digits calculated. Moore's law takes over, and in 10 years' time or so, we reach the 10,000 digit threshold, adding up terms of Mashins series. Oh, I should have mentioned, in 1949, also Mashins series was used to calculate that record. In 1961, the 100,000 digit mark was reached by adding terms of a different kind of Mashin type series, but still the same kind of mathematical idea, using an IBM 7090. And about 10 years later, we're now in the 1970s, the million digit mark was reached by adding terms of yet another Mashin type series using a CDC 600 for 23 hours. Now it's at this point, we're about to enter into the 1980s, where a new idea arises. And I should point out that in all the history that we have traversed, the over 2,000 years, there have only been really 2 ideas used for computing pi. There was Archimedes' awesome polygon idea, and there was Mashin's awesome arctangent type series idea. But now, in the 1980s, somebody has a different idea. They think to use the mathematics of Ramanujan. Ramanujan, Srinivasa Ramanujan, was an Indian mathematician who lived around the turn of the last century. And he is hands down one of the most mathematically talented human beings to have ever lived. As a young man, growing up in a family of modest means, he was a math prodigy and was not getting a great deal out of his education. But by a good stroke of luck, one of his friends lent him a library book. I'm going to double check my notes to get the title right, because this had a great effect on Ramanujan. A friend lent him a copy of A Synopsis of Elementary Results in Pure and Applied Mathematics, published in 1806 by G.S. Carr. In this book, Carr sought to summarize all of the fundamental mathematics up to that point in time. His book contained about 5,000 theorems and very few proofs. Reportedly, Ramanujan just devoured this book. It inspired him and led him to his own mathematical investigations. Sometime later, he decided to send some of his own discoveries to some English mathematicians. Unfortunately, most of those mathematicians did not appreciate the quality of the work that they were receiving, possibly because Ramanujan simply sent them a list of his results without any explanations, and these were some really unusual results. So if somebody wasn't properly trained, we might not see how brilliant they were. Adam.
Is it the case that they didn't appreciate it because they didn't understand it?
Possibly. Now, all the results that he included were of a type, they were actually infinite series, most of them. So the recipients would have understood the kind of thing that these were. It wasn't that Ramanujan was using obscure notation, but they may well have failed to appreciate how deep these things were. They might have looked like just somebody making things up. I don't know. Fortunately, in addition to these other mathematicians, Ramanujan sent a letter to G.H. Hardy, a preeminent English mathematician of the day, and Hardy appreciated that the person behind this letter must be a mathematician of the highest rank. Hardy later said that among these results that Ramanujan sent him, some of them he recognized, some of them he knew himself, Some of them he had proven himself. Others he did not know of a proof immediately, but felt that if he put in enough effort, he could prove them. And still other results baffled him entirely. But Hardy said they had to be true because nobody would have the imagination to make them up. And he was right. Hardy invites Ramanujan to England, to Cambridge, and thus begins a really fruitful collaboration. Unfortunately, Ramanujan was plagued during his entire life by health problems, and at the young age of 32, he died. Wow. An infection of the liver, I think is what fell ultimately. He left behind 4 notebooks containing a collection of his results, almost 4,000 results in these notebooks. Now, Ramanujan never intended these notebooks to be published. They contained his results, sometimes organized, sometimes disorganized, but almost always without any proof. I should explain that the lack of proofs doesn't mean that Ramanujan didn't have a proof. Certainly he did, but he might have been simply operating out of a certain tradition. At that time in India, paper was very expensive, and so school children had been taught to do their work onto like a board, and then transfer the final result onto paper. Also, Ramanujan might simply have been emulating that fellow Carr, whose book was so inspiring to Ramanujan. Carr's book contained all these theorems and almost no proofs. At my graduate alma mater, University of Illinois Champaign-Urbana, there is a great mathematician named Bruce Baird. I was very pleased to meet him during that time there. One of the world great mathematicians and the nicest guy you'd ever want to meet. In about the 1980s, Baird undergoes the Herculean task of organizing and publishing Ramanujan's notebooks. This way, mathematicians across the world could appreciate and benefit from Ramanujan's insights and hopefully fill in all those missing proofs. By now, virtually all of those 4,000 results have been proved. I should point out, you might expect some of the results to be wrong. After all, Ramanujan wasn't intending for these to be published, but in almost 4,000 results, the number that were actually wrong was fewer than 5. The highest quality work. By now, virtually all of these results have been proved, but having a modern proof of a Ramanujan result is very different from knowing how Ramanujan himself came up with it. There are a number of cases where the modern proof could not possibly be how Ramanujan discovered it. Some modern proofs are what are called verifications. This is where you make heavy use of knowing what the result is to help verify that it's correct. Of course, Ramanujan is discovering the result, and so he would not benefit from knowing what it was in advance. Some of these verifications use positively subtle and difficult algebraic manipulations, the kind of algebra that these days are done by mathematics software packages. Ramanujan, of course, would not benefit from such tools. How Ramanujan arrived at these deep, beautiful, and difficult results remains a mystery. Which brings us to 1985, and Bill Gasker has a really good idea for setting a new record for pi. He uses a formula by Ramanujan. This is now a formula for 1 over pi. Look at this thing. Oh my goodness.
Scary.
And yeah, it's scary and beautiful, I think. Just incredible that this thing on the right-hand side produces 1 over pi. And I should emphasize that the mathematics behind this is utterly different from the mathematics that have been used to compute pi up to this point. This is not a Maschin type series. How good is this series for computing pi? Each additional term gives you 8 more digits of accuracy in your approximation. To put that into perspective, the infinite series that I created by walking across the room, every time I added in a term, I cut the distance between myself and the other side of the room, the sum of the series, by a half. Every time you add in one of the terms of this series, the distance between yourself and the sum of the series is cut down by a factor of about 100 million. Wow. It is astonishingly good convergence. By the way, if this series is so good for computing 1 over pi, and it is, it's amazing, and if it's been about 7 decades since it was presented to the world by Ramanujan, which it has, Ramanujan published this in 1914, why didn't anybody else use it before now? 2 reasons. It happens in mathematics, unfortunately, that sometimes when somebody has a really good idea, the mathematical community just kind of forgets about it. And that's what happened. Ramanujan published this formula and a bunch of others for 1 over pi in a paper in 1914, and there was a little bit of interest in it initially, and then folks just kind of forgot about it until Gosper renews interest by using this formula to calculate pi. However, because folks had largely forgotten about this, and because Ramanujan, as was his habit, in his paper did not provide a proof of this result, Gosper was using an unproven formula. There was no known proof of this when Gosper was using it. However, Gosper uses the formula, symbolics 3670, computes 17.5 million digits of pi, notes that the first 10 million digits or so match perfectly the previous record for pi, and in this way produces a very substantial amount of experimental evidence that Ramanujan's formula is correct. And in fact, 2 years later, 2 mathematicians succeeded in proving this formula by Ramanujan, confirming that Gosper was right all along to use it, and several other formulas that Ramanujan used. From this point forward, almost all, not quite all, but almost all pi records are made using either this formula or one that uses the same kind of Ramanujan type mathematics. Just 4 years later, the Chernovsky brothers used a Ramanujan type series that they proved that had even better convergence to calculate, well, we traversed the 1 billion digit threshold of this. Look at the huge leap in those 4 years in digit calculation. They used an IBM 3090. There's a picture of that right there. This is very typical of the devices used to compute pi records in this era. Big mainframes, supercomputers. In 2002, Kanada and his colleagues reached the trillion digit mark by running terms. Now, this I can't explain. I don't know why, but they went ahead and went back to one of the Maschin type series, whose convergence are not nearly as good as the Ramanujan type series. But they ran it on a Hitachi supercomputer for 25 days. Maybe if you've got 25 days of time on a supercomputer, you don't have to use the best formula available. You're going to get a decent approximation. Oh, there's a neat footnote right here. In between these last 2 records, in 1996, I think I got the year right, marked the 50th anniversary of the building of the ENIAC. And in that year, as a celebration, a computer chip was made whose size was smaller than a dime that contained all the functionality of the entire ENIAC. Moore's Law. Hey, we're in the home stretch. Last 20 years. In 2011, a fellow named Kondo hits 10 trillion digits by adding terms of Chernovsky's series, as implemented in a fantastically optimized program written by Alexander Yee called Gamma Cruncher on a computer built by Kondo. So Kondo was not using a big mainframe or supercomputer. He was using a computer that he built from parts that he got from electronic stores, ordered over the internet, expressly for the purpose of computing a mountain of pi. He ran that computer for 371 days. It would have been less than a year, but at some point, can you guess what happened? It crashed. I'm not sure if it was a power outage or what, but like running hardware for like 300 some days, you might get some bad luck. So it crashed. He didn't lose all the data, but it did set him back a bit.
So I don't understand, Chris. Did he decide how long he wanted to run it for, or how many digits he was going for? Or was it like, at some point he's like, all right, I've reached what I want, and stopped it?
It's like your gas tank, because you went over 50.
Right?
He's tried to stop.
Right? Like maybe
Yeah.
I actually don't know the answer to that question. Christine, that excellent question. My suspicion is that he was aiming for 10 trillion digits.
Right, right.
I've skipped a few records in between, but I think he knew that's a nice clean number. Not sure about where the 50 came in, but
To be safe.
it would get to be safe, and knew that that would set a record, and did not know in advance how long it would take. Yeah.
Maybe it crashed at 50 and he's gonna start at 10%.
Pardon me?
It probably crashed at 50 and then he had to start his program again and ran over 10 trillion. Who knows?
I don't think so, but that's good. This is a picture of, in case what you're wondering what a computer looks like that is assembled expressly for the purpose of computing a mountain of pi. This is Condo's custom-built computer. I read the technical specs for this and made almost no sense to me. I really don't know computer hardware, but I did notice that among the maze of wires, there are 19 2-terabyte hard drives. Each one of these holds 2 trillion bytes of information.
Wow.
Because if you're going to calculate this much pi, you need a lot of storage.
I don't understand how he was able to run it for 370 days. Tech support tells me I have to reboot my computer every like week or something.
Or at least change your password.
This is the advantage of building your own computer. Because then you have a computer that doesn't say, hey, update me, or whatever. This brings us now to the most recent record, set just last year. A team operating out of Switzerland reached 62.8 trillion digits, set the current record. By the way, we were musing over what the plus 50 was in the last record. This funny looking number is actually exactly the nearest integer to 2 pi times 10 trillion. This is why they picked that number. So pi is about 3.14. 2 pi is about, 2 pi is about 6.28. 2 pi times 10 trillion. And they calculated this basically in the same way that Condo did. Same software, similar hardware, but more storage. And that helped them to cut down the time to only 108 days. This actually would be a really superb place for me to stop the talk as a natural ending point, the current record. But I really would, if I could borrow just a few more minutes of your time, I wanted to share with you that despite this incredible success that there's been in calculating the digits of pi, there are some really basic questions about the number pi for which we don't yet have an answer. To motivate one of those questions, let me share with you a few slides that show thousand-digit segments of the number pi, each one substantially deeper in the decimal expansion than the previous one. After I show these to you, I'm going to ask you a question. This is the first 1,000 digits of pi. And here are the digits starting just after the 10,000th, 1,000 digits again.
Did you type that out?
Nope. Copy and paste, my friend. Here we are now, 100,000 digits in. A million digits. 10 million digits deep in decimal expansion. 100 million digits. And 1,000 digits that are 1 billion digits into the decimal expansion pi. Now, what do you notice?
7.
What comes to mind? 7? In this slide or the others?
And lots of the slides.
Like double sevens.
That may be due to the fact that the human eye is good at sort of picking out patterns, and maybe for you, like 7s kind of stand out against the other digits.
Maybe.
They're straight and don't have the bends of many of the other digits, perhaps.
There's a lot of eights.
In the same way, yeah. Do you think, Patrick, that there are more 8s than there ought to be? More 8s on average than 0s, 1s, 2s, 3s on the other digits?
I would say so.
Maybe there's like a preference for the number 8s? Perhaps. The decimal expansion, actually, interestingly, according to all the measurements that are made with the digits that are known, shows a number that appears to have completely random digits. It's fascinating that although pi is not, the digits of pi are not random, they're the opposite of random. They're exactly what they need to be the ratio of circumference to diameter. But they have every appearance of being random. They pass tests for randomness with flying colors. Despite that fact, there is no proof that this random appearance continues. No one has been able to show that that is decisively true. There's a technical idea in mathematics that captures randomness mostly. It's called the idea of normality. A normal real number is one in which there is no preference for any one digit over any of the other digits, and there's no preference for any pair of digits over any other pair, and so on. It is universally believed that pi is a normal number, but no proof has been forthcoming.
So you're saying that in these 10 billion digits, what's that, how many digits do we know?
62 trillion?
62 trillion digits, that if they like look at how often the digit 8 comes up, it's 1/10 of the time?
It is super, super close to 1/10. Not
And
exactly.
every single, like all the digits are essentially 1/10.
Incredibly, incredibly close. I've seen the stats, and it's really, really striking.
Wow.
Yeah. It's very nice. It has all the appearance of just a random mess of digits, but again, of course, it's not. But actually, in terms of the folks in my profession, their embarrassment gets worse. Not only can we not prove normality, we can't even prove that each of the digits, 0 through 9, appear infinitely often in the decimal expansion. For all we know, at some point, deep in the decimal expansion of pi, we stop getting 2s and 3s and 4s and 5s and 6s and 7s and 8s and 9s, and there are only 0s and 1s from that point on. It would be ridiculous if that happened. There is no proof to guarantee that it does not. And with that, let me thank all of you. It has been wonderful. Please come to our Pi Day celebration. Come to the north side. Questions? Yes.
Can you repeat the questions for the people on Zoom?
Absolutely, I will. Thank you.
Yeah, I just was wondering, with the age of supercomputers, there was a great deal of competition for time with those supercomputers. And what prevalence did pi get? Like the investigation of this pi number and stuff like. How important was it enough that they garnered all this time on these supercomputers?
Well, I don't know if I can address that question directly, unfortunately, about how important it was. Definitely, as we saw, there was a span of time when these big mainframes were getting used, and not by everyone necessarily, although you can understand the temptation. If you're working at a place that has a giant computer, why not calculate pi? But interestingly, there is another connection between computers and pi. One might ask, what is the point of all of these digits? Like, is there any value to it? And actually, routinely, new supercomputers are tested, once they're built, by computing, let's say, 1 billion digits of pi, using one of the formulas. Because in order to calculate 1 billion digits without an error, you've got to have a pretty perfect structure in your computer, a pretty perfect hardware. So it is used to test computers. So in that sense, it's kind of common. Other than that, I'm afraid unfortunately, I can't address the question. Yes, Adam.
So if I want to summarize this so that I understand this, because I saw the mathematicians and physics people in here when you were going through this history, and they were riveted. I mean, the rest of us were really kind of paying attention, but this was foreign to us. But the mathematics and physics people were in here like, ooh, you can just tell. There's like a little drool coming down their mouth. So,
Like seeing old friends.
right, yeah, exactly.
Wait, not everybody feels that way?
Yeah, right. And for some of us who are not in that math geek world of this is amazing. I am still of the position that and I'm sure a lot of people in academics are we have this. I want to know the answer. I want further truth. That's what I'm looking for, and I get that piece. But I think like you, I was thinking basically, okay, aside from those two things, what's the value? Like, how does this contribute to something? Is this now this new extra, billion pieces of pie? Does this help us build a rocket ship or something like that? But it sounds like to me it's a check. They use it. They use this phenomenal piece of information that people are just curious about to check that computers are working correctly.
Yes, and so Adam was just asking a some question about, continuing the theme from these gentlemen, about the value of all these digits of pi that have been calculated. Yes, it is routine. Calculating pi is routinely used to check the hardware of new supercomputers. There is another benefit or plus here, Adam, which is that sometimes the value of a mathematical result can be in the quality of the mathematics that was used to create it. And so the math that goes into these records is just gorgeous, deep mathematics. Absolutely worthwhile. And so it is just lovely to see, and Ramanujan's work getting appreciated even more thanks to, I don't know that Ramanujan would have computed anything more than, I think maybe a dozen or 20 digits of pi just for his own amusement back in the day. I don't know that he anticipated that one day his formula would be the basis of a whole new era of pi calculation. So there is that kind of theoretical benefit.
I don't know, you sound like my students. Why do we care?
Is this something I'm ever going to use in my life?
Is it on a test?
Because it's beautiful.
Well,
Yes.
we still don't know the 101110011 question.
Right.
Right? So-
Right, no, because that could be a reason to really go after it, to be that person that finds out that there is at the end, it does repeat. And all you people that thought that it wasn't going to repeat because it looked so
No,
random, screw you
It
guys.
can't repeat. If you have been paying attention, it's been proven it can't
It's already
repeat.
knowing that it does not repeat.
Yeah.
Not possible.
See how they're talking to me like I'm a child?
Yeah, just to follow up on Christine, yeah, there is a mathematical proof using calculus that it does not repeat. Not only does not appear to repeat, but it really will never repeat. More than that about the decimal expansion, as I've highlighted, we embarrassingly don't know.
We're also getting more closer to calculating the perfect circumference of a circle.
You just reminded me of a nice little observation that connects with these other questions about the value of this. So, one can argue that the number of digits of pi that you actually need to measure circles is about 42, because with 42 digits of pi, you can calculate from using the diameter of the known universe its circumference with an error of less than the width of a single proton.
Wow.
So one can argue that all digits past the 43rd or past there, has no practical value for measuring circles.
That is a good answer. I like that answer.
Start memorizing them.
And on that note, another round of applause for the Math can be very exciting, especially when you pair it with some tacos and beer. I want to remind you that our April speaker is going to be Xiaoling Zhang. He's going to talk to us about Earth Day. And I think something to do with the My Food Plate. She might work that in. So it should be very interesting.
Bring the kids.
No, don't bring it.
Learn about nutrition.
Yes, it's something with nutrition. So it should be. Thank you very much. Awesome.
Thank you for coming, guys.